In 1969, Ken Thompson of Bell Labs had an idea for a new kind of file system which would be more uniform than any comparable file system before then and would be simple to implement, simple to use, and powerful. It presented a uniform hierarchical view of the entire file system and supported the same operations on all types of files. After experimenting with this file system, he and several others went on to implement the rest of an operating system, which became Unix. There's an article by Dennis Ritchie and Ken Thompson called The Unix Time-Sharing System, available on Dennis Ritchie's webpage at Bell Labs, specifically at this URL, with discussion of the Unix file system starting on page 2. Compared to the state of the art at the time, this file system was, first, completely uniform. The master directory, which we now call the root directory, the user directories, subdirectories, and all organization of system files is all done using one simple hierarchy of directories. This means that users can make their own subdirectories just the same as system ones. So we get a directory tree. We can specify a file name in the tree with a path name, which tells us how to get there from the root. Directories are just a special kind of file. If you want a directory listing, you just read the file, which is that directory. No restrictions on file names and no system interpretation of file names. File names can be any sequence of characters. Periods are not special. Upper and lower case are considered different. There are only two characters you're not allowed. A slash, because that will be used to separate directory names in a path name, and the 0 byte, not the character 0, but ASCII null, because that will be used to indicate the end of a file name or of a path name and marks the end of a C string as passed to the operating system. All of the available disks are integrated into one uniform file system. I might have a file called user_agr source hello.c, and that might be on a different disk than your file called user_u hello.c. But a new disk can be associated with one portion of the directory tree, and it is seamless to users specifying file path names. A disk or a disk partition is mounted at a certain point in the file system. In the simplest case, if you have your own disk partition, it could be mounted as /user/u. Then the root directory on that disk becomes user_u in the whole tree. Therefore, it's easy to specify other people's files. Once you can refer to other people's files, you need an access protection capability. You have to be able to specify who is allowed to do what to which of your files, read them, write them, delete them, and so on. Unix has simple file modes to accomplish this. See the change mode command. There used to be a lot of computer programming issues around file records and around random access versus sequential files. If you were going to be jumping around in your file, like in a large database where you want to read record number 1,000,006 without having to read the first 1,000,005 records first, you would have to specify that a file was a random access file, which would make jumping around faster, but sequential access slower. In Ken Thompson's file system, a file is just a list of bytes. The operating system has no involvement in the format of the files, and it also provides for easy random or sequential access to any file. This is the Unix file system. Like nearly all of the other fundamental parts of the architecture of the Unix operating system, the file system is based on a few simple but powerful ideas. The kinds of ideas that take a long time to construct and to get right, but when you've got it designed right, you know you've got it right because the result is simple and straightforward and powerful. Any file system is basically a complex data structure on disk. The starting point for the Unix file system is the inode. I stands for index. This is an index entry for a single file on the disk. A disk holding a Unix file system contains a bunch of inodes and a bunch of data blocks. Each inode represents one file. Not necessarily a plain file. Each directory gets its own inode too. A directory is a list of records or structs, or pairs if you prefer, which are simply a file name and an inode number for that file. Here's an example ilist the list of all inodes. The numbers on the left do not actually appear on the disk, we just have a big list of inodes in order, an array. As well, the contents of the file is in the data blocks, not the inode. What is in the inode is the location of the data blocks, which are the content of that file. The inode contains a variety of data, which we'll discuss shortly. Directories' contents are much less substantial than the inode information. The contents of a directory is simply a list of pairs, or structs of two elements, which are the file name and the inode number for that file. For example, the root directory here, which is always the file contents pointed to by inode number 2, contains 3 records which say that the directory contains 3 entries. User, which is inode 7, etc, which is inode 4, and bin, which is inode 6. This therefore represents this directory tree. We call these inode entries links. We can get to a file because it's linked in to the file system somewhere. We identify a particular file by giving a path name, which is a sequence of directories to traverse until you get to the desired file. This target file, like any file, might be a directory, but the intermediate nodes in the path must be directories. For example, the hello.c near the lower left of the picture can be identified as user AJR source hello.c. Since the path name begins with a slash, it starts from the root of the tree at the top. This is called an absolute path name. Alternatively, if we do not begin with a slash, we start from the current directory, which you can change with the cd command, as you know. This is called a relative path name. Suppose I want to have another name for the date command, /bin/date, inode 9. I can call it xyzzy in the current directory by executing the command ln/bin/date xyzzy, ln for link. This creates an additional link for the date command. Look at the ls-li output, where -i means also tell me the inode number. The extra column on the left is the inode number displayed because we said -i. These two items have the same inode number because they are the same file. The file system is no longer a tree, although the directories in the file system still are a tree. We can also note that the link count, the third field here, is now 2. There are 2 links to this file. There is only one actual file involved, although it is in 2 different directories. The only thing actually in the directory is the file name, so all of the other ls-l information is the same. The protection, owner, size, times, and data block references are all in the inode, inode number 9, not in the directory it is linked into. With the current directory concept, you want to be able to specify the current directory as a file path name. For example, if you run ls with no arguments, that means to list the current directory, it calls opendir, and it needs a path name to pass to it. So we have a convention. In every directory, you have a dot entry, which refers to the directory itself. It also turns out to be convenient to be able to specify the parent directory. So we also have a convention that in every directory, you have a dot entry, which refers to the parent directory. For the root directory, in designing the Unix file system, they could have omitted the dot directory entirely, but they chose to make /... be slash itself, like this. So, what data is in the inode? Not most of what we see here. Most of what we see here is a statement of the contents of the files pointed to by the various inodes. The only data here which represents the actual inode contents is that D meaning directory. In addition to that one bit of information saying whether or not the file in question is a directory, and the link count, which we've already seen, the inode contains the mode, the protection stuff, owner of the file, or user ID, UID. The owner can change the mode of the file, and whether or not you are the owner also affects the interpretation of the mode. Group, or GID, similarly affects the interpretation of the mode, but no effect on who can change the mode or even who can change the group. And times. There's a last modification time, or M time, a last access time, or A time, and a last inode change time, or C time. These time values have a simple format, just the integer number of seconds since a fixed starting date and time. Not the file name. For example, a file linked into the file system in two places can have two different names, as we saw with the date command. And location information. We number all of the blocks on the disk, not track sector numbers if you've seen that, just numbers from 0 up to whatever. We will store these block numbers in the inode so that the operating system knows where to find the data blocks of the file. 10 block numbers right in the inode point to the first 10 blocks of the file, blocks numbers 0 through 9 of the file. Another block number is the number of a block which itself contains 128 block numbers for blocks number 10 through 137 of the file. We call this the indirect block. Then we have a double indirect block. It's the number of a block containing 128 block numbers, and each of those block numbers indicates a block containing 128 more block numbers for 128 more blocks of the file. This is the double indirect block. Finally, we have a triple indirect block. The exact details here aren't important, but the basic idea can be seen to be quite different to a chained system in which the inode contains just one data block number, and then that data block contains 1016 bytes of data plus one more data block number, and so on, each data block chaining to the next data block. That seems much simpler, and it is traditional, but it has a serious drawback. Note that in the Unix file system, no matter how big the file is, there is a small bounded number of reads to get to a given byte number. For example, if we have 1024 byte blocks, byte number 20,483 is byte number 3 in block 20. This will be the 11th entry in the single indirect block. So we can read it with 3 disk accesses: the inode, the single indirect block number, and then the block of the file. If we need to go into the triple indirect block, we would have 5 disk accesses, but we never have more than 5. Whereas in a chaining system, in the extreme case, we would need 22 accesses to read block number 20. First read the address of block 0, then read block 0 to find the address of block 1, and so on. Now, if we're reading a file sequentially, this is not a problem. We will have read block 19 before we go to read block 20, so we'll have the chaining address already. But if we're jumping around arbitrarily in a file, we start to pay huge performance penalties. And that's exactly why other file systems around that time had several different file types. They were good at different things. By making the Unix file system good at both random access and sequential access, they made the whole thing much simpler for the user of the file system. The Unix file system is a reasonably simple way to achieve a number of objectives. Simplicity is good. This is a recurring theme amongst skilled computer programmers, and it's embodied very heavily in Unix. In addition to plain files and directories, we have something called the device files. We don't need physical location information, so we're going to put major and minor device numbers in the inode instead of that. We look at our TTY. There's a handy command TTY which figures out the device file name for the terminal we're on. So if we look at this file, We see in the middle there that 16, 0 are a major and minor device number. 16 identifies a device driver in the kernel. 0 is a parameter to that so that all sorts of different TTYs can use the same device driver code parameterized. Other than that, though, it's a normal file in the file system. It has an inode number. We can use hierarchical names. We can use protections. You see the file modes there. You can link to it for convenience and so on. You may notice that this file is writable by group TTY. What's that about? Well, let's look at the write command. We see there the 7th character from the left, that S, indicates that this file is executable, but also has another bit set in the mode called a setGID bit. When you run this program, you are temporarily a member of that group. So, if I say write to AJR, then it can send a message. And even if I can't write to that terminal, dev ttys000, because of the protection, while I'm running the write command, it can temporarily write to it. But it is set GID to TTY, so if I don't want to receive messages, since I own dev ttys000 so long as I'm logged in, I can change mode that file to prevent other people from writing to it. So that's the idea behind device files. And device files are in the file system, so we could have a hierarchical name like, for example, dev tape3 could be a device file. You could make a normal directory /dev/tape and put in there device files for different tape drives. Once we have this, a program can be expecting a file. You give it a TTY or a serial port or a printer. Device files are files. I'd also like to mention one particular device file known as /dev/null. This is a very simple device driver in the operating system kernel that just does nothing. If you write data to it, it is discarded. If you read from it, you get immediate end of file. We've seen the use of this in shell scripts in discarding data from commands that insist on writing to the standard output or standard error, but we don't want to see it. We can redirect it to dev null, and it is discarded. Dev null is also very useful as a default I/O destination for any of the standard I/O channels, standard in, standard out, standard error, if we want to prevent a program from interacting with those channels, or if it is run in some context where there's no obvious default file to connect to those channels. Symbolic links. This was an addition to the Unix file system in about 1980. Everything I've said so far in the video was part of the original design. We will call the existing kinds of links hard links for clarity. Now with hard links, two links to a file have equal status. If you remove one, the other one stays. Create a file, make a link. Now we have two names, but as we can see, they're both the same inode number, and they're the same file. They don't just have the same contents, they are the same file. Here's another way in which we might modify a file. Let's uppercase the file using the software tool TR. The sequence of operations broke the connection between the files. That's unavoidable sometimes, and we actually do sometimes want a facility to give one access path to a file an inferior status. So we have this idea of symlinks. There's a special bit in the inode. It's not a plain file or a directory, but a new thing. The file data content is a path name to the pointed to file interpreted by the operating system kernel. We say ln-s to request a symbolic link instead of a hard link. We see from the differing inode numbers that these are different files. We also see that file2 is a pointer to a file in a way that can be read by ls and is read by the operating system when, for example, in the previous command, we read from file2. If we replace the contents of file, this looks the same. File is changed. File2 is not. It's still a pointer to file. But let's do our TR example. Since we modified file, and since file2 is a different file, file2 still points to file, whatever might be under that file name at this point. I've heard that at a meeting about introducing symlinks at the University of California at Berkeley, Dennis Ritchie suggested that when introducing symlinks, user-controlled hard links should be removed. I think that the subsequent confusion over these two similar but completely different concepts suggests that he was right, although each does have its own interesting uses. One interesting difference is that symlinks can cross file systems, since they specify a path name that's interpreted on its own merits. Hard links can't cross file systems because any inode number would be understood as referring to that inode in the same file system. The specifics of our description in this video of the direct block, indirect block, and so on gives us a maximum file size which is just under a gigabyte. Since gigabyte disks were unheard of at the time, this was not a problem. Subsequent allocation schemes have wasted a bit more space on small files, with the result that the limitation is usually 2 gigabytes these days. Still, this isn't good enough for some tasks. So many modern versions of Unix have changed the system around a little to get a larger maximum file size. Although some haven't, this scheme doesn't prevent disks being more than 2 gigabytes, just a single individual file. Anyway, the changes are pretty straightforward. You can make that single indirect block a double indirect block. You can make a double indirect block a triple indirect block. Just don't lose the bound on the number of reads, or you no longer have random access. An interesting programming exercise on the Unix file system is to write the pwd command, which outputs the absolute path name of the current directory. The algorithm is to read ... and look for the current directory's inode number, and then do this iteratively up the directory hierarchy until you reach the root.